All right, let's start this again. Okay, so here you go. The other now we can also in certain material in the lab. What we like to do is we like to figure out what the resistance of certain materials are going to be, or test for their resistivity. In other words, we can run a current through them. We can we can plug them up to a voltage, run a current through them. So we've got something that kind of looks like your uh, homework problem here. This homework problem. Notice the different um, the area the area divided by the length. And here the area is different. The smaller length, smaller area, longer length this way, and then this way it's 2L going. The length is 2L with this same area up here. So in other words, you might be going, "What the hell was all that?" I'll show you. I'll tell you. Okay, but first let's talk about this equation right here, which is this. So to find the resistance of a certain metal, it's got to we need to know its resistivity. Then we take the length divided by the area. Okay. So look at these three cases. So let's leave the resistivity constant. All right. So let's say I consider resistance if charge was a human being, how it would consider going through a cave or a tunnel or a hole. Okay. It's got to crawl through there or walk through there. So in other words, if I'm walking along, and my resistivity is the same, to how claustrophobic I am or something, and I come up to a long, dark tunnel, okay, I come up to a long, dark tunnel, and the area is not bad. Okay, so what happens to my resistance? My resistance gets huge. I don't want to go through there. It's going to be hard to get me to go through there. Same thing happens if my resistivity, my claustrophobia stays the same. I go up to a medium length dark tunnel. Okay, not bad. But the area is really small. I'm going to be like, I got to low crawl through that. I got to get on my belly and crawl through this thing. My belly, man, that thing better be pretty damn wide. But anyway, going, small opening. I don't want to go in there. Resistivity gets huge again. On the other hand, resistivity, L, the length of it, okay, the length of it, and then it's got a big area, then the resistance goes down. All right? So a big thick wire has low resistance. So the charge flows freely and it doesn't heat up. All right? But here's what happens. Here's what happens. People, especially this time of year, like even this morning, classic example. So again, I always like to have where science and social justice, especially when we're talking about electricity, intersect. All right, you're going to have fires, and fires usually happen in the poorer neighborhoods, where the heat might be getting turned off because they don't have a job and they're trying to now it's against the law for KCP&L to turn off the heat when the temperature is a certain time, but our temperature is fluctuating so much that they can go, okay, yeah, your heat's on now, but tomorrow as soon as it gets to 50 degrees, boom, we're turning it off. So what do people do? They buy a cheap ass space heater, okay? And when they get the cheap ass space heater, what happens? It's got a resistivity, probably pretty low resistivity, and then they get a small little cord, a really small cord, with kind of with an average, area, and so it's got small resistance. R is small. And that means it's going to heat up. And that means it's going to melt the plastic. And that means it's going to be on a frayed rug. And that heated plastic, that melting plastic on a frayed rug starts fires. It's all physics. But how we keep that from happening is social policy and watching out for the poor. Anyway, sorry, didn't mean to get on my soapbox here in the middle of a physics lesson, but everything is interrelated. Okay. All right. So, looking at this equation here, now let's go to this homework problem. Let's see what it says. There we go. The resistance. Here's three situations. The drawing shows three situations in which the current takes different paths through a piece of material. Each of the rectangular pieces is made from a material whose resistivity is equal to 1.5 times 10 to the negative 2 ohm meters. Okay, so it's not a very that's a pretty high resistivity. So it's not a very good conductor in the first place. And the unit of length in the drawing, LO, is equal to 5 centimeters. Okay, so I'll just do problem 1. Okay, so problem 1 looks like this. 5, okay, let me write down the things. 5 is 1.5 times 10 to the negative 2 lambda times meters. That's resistivity. L naught is equal to 0.05 meters. Okay. Okay. So we're looking at this one, where the front view. I'll let you see what I'm doing. Where the front view is equal to this. 2 times 1. They didn't draw this to scale very well, did they? If I'm looking at it this way, and then it goes back 4. So the length of it is 4 L naught, where the height is L naught. So the area is equal to, the cross-sectional area that this thing is going to go through is equal to L naught times 2L naught, which is equal to 2 times L naught squared. The length is equal to 4L naught. Okay? So the resist, because the current's going to go this way. It's got to go that length. The area is not bad. Okay, the area is not bad. So R is equal to the resistivity, whatever that is, times 4L naught divided by 2L naught squared. So R is equal to rho times 4 over 2L naught. So this is equal to rho times 2 over L naught. Oh, shoot. I'm sorry. So this is what the area is equal to. L is equal to 4L naught. Here's the cross-sectional area. Here's how deep it went. Sorry, I didn't show you. See, this is when you would have barked out in class and said, hey, dummy. So there's my resistance. And so the current then, V equals IR. You could either calculate that if you wanted to already, or you could just set up for this scenario only. Then V is equal to I times 2 over L naught. So we multiply by L naught over 2 on both sides. And so the current is going to equal V times L naught over 2. Whereas this is going to be, 2 rho. Yeah. All right. There you go. We'll stop there. And now we're going to look at the change in